Alright, now we're moving into Chapter 8, which is all about sampling distributions. Sampling distributions are necessary to understand confidence intervals, which we'll be getting to in the next chapter. The first sampling distribution is when you're dealing with the sample mean. A sampling distribution in general is the distribution of a statistic, remembering that statistics are like your x bar, s squared. Later we'll get into p hat. And those statistics are used to make predictions about the population parameter. So like for the mean, the statistic is x bar, the parameter is mu. So what you do is you find the probability distribution for all possible values of the statistic to get the sampling distribution. For the sample mean, that sampling distribution of the sample mean x bar is the probability distribution of all of the values of the random variable that are computed from a sample of size n from the population with a mean that you know and a standard deviation that you know, which is very formal definition, and here's what it's trying to say. If you want the sampling distribution, what you would do is you would take a simple random sample of size n, and then you get the sample mean for whatever that variable was that you were collecting the data on. So let's say you were trying to get the average weight of individuals in your sample. So you would take a sample, let's say of size 10, weigh everyone, and get the average and keep track of that. Then you would get a new sample of 10 different individuals and compute the sample mean for that group. And you keep doing this and doing this and doing this until you have all distinct, so no overlap, simple random samples of size n. And then you make a probability distribution based on those. We'll never actually have to go through this process. I just want you to understand where it comes from. So with the mean and the standard deviation, if you have a sampling distribution and you're talking about x bar instead of x, you think of the mean a little bit differently and the standard deviation a little bit differently. To find the mean, you actually just use the population mean to estimate the mean for x bar. The standard deviation changes. You take the standard deviation for the population and you divide by the square root of the sample size. So as that n value, the sample size increases, the standard deviation will get smaller because you're dividing by a larger number. And what that means for us is that larger sample sizes produce better predictions because your standard deviation is smaller, which means your overall spread of data values is smaller. The standard deviation is also sometimes called the standard error of the mean. So those two phrases can be used interchangeably. You just have to know they mean the same thing. If you are asked to describe the distribution of x bar, you would want to talk about the shape, the center, and the spread. The shape is always going to need to be normal. If it's not normal, then we can't really do anything. And one of the ways to tell if x bar is normally distributed is if you know your original population is normal. So if your random variable x would have been normally distributed, then x bar is automatically normally distributed. So let's look at the IQ example from the last section. IQs are approximately normally distributed with a mean of 100 and a standard deviation of 15. To describe the sampling distribution of the mean for a sample of 10, what you want to start with is, since IQ is normally distributed, we know that the average IQ is also normally distributed. The center, or the mean, is going to be the same as the population mean. So the mean for x bar is still 100. The standard deviation is a little bit different. You start by taking the standard deviation from the population of that 15, and you divide by the square root of your sample size, so the square root of 10. When you calculate that out, you get 4.743. You'll normally be told how many decimal places to keep. I'm keeping all 3 of those. If you want to find a probability for x, remembering x is your individual random variable, so for one person. The example would be for the distribution of IQ scores, find the probability that a randomly selected individual has an IQ of 110 or higher. The word individual is very important here. That tells you you're still using X. So we're looking for the probability that X is greater than or equal to, that should say 110, not 120, which I fixed in the notation with the Z. Okay, once you have your X, you change X to Z using this standardizing formula we've been using. Your X value of 110 minus the mean for the population of 100 divided by the standard deviation for the population, which is 15. That gives you a Z value. Z is greater than or equal to 0.67 when you round to 2 decimal places. And you go to your normal distribution table, and since this is a greater than or equal to, we look up the opposite Z on the table, and like we learned last chapter, and we get an area or probability of 0.2514. What that means for us is that the probability that an individual has an IQ greater than 110 is 0.2514. If we would take a sample of 100 individuals, we would expect about 25 of them to have an IQ that's greater than 110. So we want to do the same general thing, but using X bar instead of X. So the example changes just a little bit. For that distribution of IQ scores, we want to find the probability that a simple random sample of n equals 10 results in a sample mean greater than 110. Sometimes you might also see the word results in an average greater than 110 or an average IQ score greater than 110. The word average or the word sample mean tell you that you're using X bar instead of X. So I set up my notation this time with X bar instead of X. X bar is greater than 110. And I still change X bar to Z. However, I need to use a different standard deviation. The mean is the same for X bar as it is for X, but the standard deviation was at 4.743 from the earlier slide. When I calculate that Z value, I actually get a much larger Z value this way. Z is greater than 2.11. Again, since it's a greater than, I use the opposite. So when I look up negative 2.11 on my normal distribution table, I get a probability of 0.0174, which is much lower than what we got for individuals. What this is saying is the probability of obtaining a sample mean IQ that's greater than 110 is approximately 0.02, which is actually unusual. We should not expect groups of 10 people to have an average IQ of 110 or higher. If we would take 100 simple random samples of 10 people, we should expect about 2 of those samples to have a mean IQ greater than 110, which is pretty low. If you don't know if the original population was normal, or let's say they tell you the original population is skewed, how do you know if you can use the normal distribution? X bar, we already talked about this. The mean of the sampling distribution is always going to be equal to the underlying population, no matter what. The standard deviation is always going to be equal to the population standard deviation divided by the square root of the sample size. No matter what the shape of the original population was, if the sample size increases, X bar is going to become normal. The test that we check for is to check if n is at least 30. If the sample size is at least 30, then we can say that the distribution of X bar is normal. So we will either look for them telling us that the original population was normal, or we need the sample size to be greater than 30. It doesn't have to be both of those things, just one or the other. So another example, we have the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. So we don't know that the population is normal. We actually know that it's not. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2 pounds. We want to check, does this result suggest anything unusual? So here's how we start out. Since the doctor used the mean weight of the sample, we know that we're looking at X bar, not at X. It's looking at that group of 35 people and their mean weight. Because the sample size is 35, and that's greater than 30, we know that X bar is approximately normal. We also know that the mean for X bar is 30 because it's the same as the population mean, and we can calculate the standard deviation for X bar by taking the population standard deviation of 12.9 pounds and dividing by the square root of the sample size, square root of 35, and I got 2.18 when I did that. The observed sample mean, what the doctor observed was that sample had a mean weight gain of 36.2 pounds. That value is actually greater than the known population mean. So we want to figure out if it's unusual for that mean weight gain to be 36.2 pounds or higher. Since we're above the mean, we want to stay with numbers above the mean. So we find the probability X bar is greater than or equal to 36.2 by changing that to a z-value, same way we always do. I got z is greater than or equal to 2.84. Now we know that any standard deviation 2.5 or higher is considered unusual. So I could stop here and just say I know that's unusual because z is more than 2.5 standard deviations above the mean. I can also find the probability using my table, and I get a probability of 0.0023, also unusual. So the probability that the average weight gain for a sample of 35 women is 36.2 pounds or more is really low. We should probably look at additional studies to figure out if income, since they did mention that these 35 people were low-income patients, we would want to check if income has an impact on average weight gain during pregnancy. Okay. If you want to have a list of steps to follow when you're doing problems about the sampling mean or the sampling distribution for X bar, here's a list of what you can do. You identify the population mean and standard deviation, find the sample size, and figure out if you're allowed to use the normal distribution. You know that by either seeing that the original population is normal or by checking that the sample size is greater than or equal to 30. Then you want to find the mean and standard deviation for X bar using the formulas. Write a probability statement about X bar by interpreting the question that's in the problem, changing X bar to Z, and then using the standard normal table to find your probability. That probability, you might be asked to interpret it. You can refer back to the examples I did for some help with that. Okay. We did some in-class practice on a worksheet. You don't have to worry about this part if you already turned it in. And I'm going to stop here and make a new video for 8.2.